So welcome to the last topic in IGCSE Triple Award Physics, okay, Cosmology, which is part of the space unit. So let's begin with a starter. On post-it notes, write down your ideas or even questions about how the universe began. What was before, for example, what will happen, how it will end. Stick your post-it notes on the whiteboard or on your wall, I guess, if you're doing it at home. If you can, come up with what a definition of a theory is, which we will look at in more detail later. So these are the learning objectives, basically describing the past evolution of the universe and the main arguments in favor of it, explaining the Big Bang Theory and the supporting evidence, describe applying the Doppler effect, this time to light waves and space, using the following equation to determine the Doppler shift, describe the concept of redshift, and explain why redshift in galaxy provides evidence for the expansion of our universe. Okay, so what ideas do you have? What do you think? In pairs, discuss how you think the universe began and how it developed. What other ideas do people have around the formation of the universe and why, and where do those ideas come from? Okay, so what is a theory? We often talk about a theory in science, but what does this word actually mean? Okay, so thinking about scientific theories you know, and how strongly do you think these theories are supported by evidence? Okay, so discussing theories around basically things that haven't been proven, or how do theories change in science? A theory is essentially an attempt to explain phenomena in our universe. Theories aren't actually proven, but they can be disproven. That's called falsifiability. Okay, if a theory is disproven, then we look for another explanation, or we develop the theory. The theory gains evidence that supports it, then it becomes strongly accepted by scientists, and therefore becomes the dominant theory to explain things. Okay, so a theory is essentially an explanation of a phenomena. So today we're going to focus on the Big Bang Theory. So what is this and what does it actually explain? No, it's not the TV show. However, it begins at the start, in the beginning. So 13.7 billion years ago, a tiny fireball of infinite density exploded. Intense heat and light flew out in all directions. After about 300,000 years, the temperatures cooled enough for atoms to begin to form, and clouds of hydrogen and helium gas formed. So several billion years later, matter began to contract, creating the universe as we see it, with its stars and galaxies. Our galaxy, which we know is called the Milky Way, formed about 10 million years ago. So what does the Big Bang Theory actually predict? Well, the theory states that to begin with, all of matter in the universe was concentrated into a small, incredibly tiny point, called a singularity. This began to enlarge rapidly in a hot explosion, which we now call the Big Bang, and the universe, according to this theory, is still expanding today. So it's important to note that the Big Bang Theory does not explain anything that happens before the Big Bang, only the origin and what happens after. Therefore, it only explains the evolution of the universe from this point in time, from its creation. So the idea of the expanding universe. Okay, so we start off with the Big Bang here, okay, and we go through in time. So another way to imagine the expansion of the universe is to observe what happens when you blow up a balloon. Okay, so here has the expanding universe, and this is like a balloon. Okay, so if you put dots or crosses on the surface of the balloon, then these dots, when they're placed, on the surface, over a period of time, the balloon expands and the dots all move away from each other. Okay, in this model, the balloon obviously represents the universe, increasing in size as time passes. The dots or crosses represent galaxies that are seen to move away from each other as the universe begins to expand. Okay, so obviously these dots are now moving further away from each other on the surface of the balloon, which represents the galaxies. So how do we know the universe is expanding? Well, we use the electromagnetic spectrum and the idea of waves, which we've already touched upon. So all objects above absolute zero, negative 273 degrees Celsius, emit electromagnetic waves. And there are lots of stars in the universe which are emitting lots of electromagnetic waves. This is important as it helps to explain the evidence behind the expanding universe. Okay, so we know a source like a star will emit electromagnetic waves in all directions, so we expect their wavelengths, the emitted waves, to stay at a constant. Okay, boom. Okay, they're moving. If the source of the waves is still, then yes, the wavelengths and frequency will remain constant. Okay, what would happen to the wavelengths and frequency if the source actually started moving, like planet Earth, for example? What can you see happening? Okay, so it's like the Doppler effect, basically. When a source moves towards an observer, the observer's wavelength decreases and the frequency increases. When a source moves away from the observed wavelength increases and the frequency decreases. This is known as Doppler shift. Okay? So in terms of the expanding universe, you should see something called redshift. So when a source, okay, and we'll call this source here, this particular star, okay, star X, okay, is moving away from the observer, okay, the rubber ducky on planet Earth, which is also moving, the observed wavelength increases and the frequency decreases. Okay, so you've got an increase now of this wavelength as it moves away. If the source emits yellow light while moving away from what side of the light spectrum will it shift to? Okay, so it's going to get a lower frequency, okay, and a wavelength increase. Okay, so we start off with yellow light, and obviously as it gets lower in its frequency and its wavelength, it's going to move towards the red end of the spectrum. Okay, that's known as redshift and evidence in some small way of the expanding universe. This is known as Doppler shift. So there is actually a calculation to look at Doppler shift, and there's two types of Doppler shift. A redshift, or a shift to a lower wavelength away from the observer, which we saw in the last slide, or a blue shift, or a shift to a higher wavelength towards the observer, which is known as a blue shift. So you'd see the light basically moving towards the blue end of the spectrum. Anything that emits a wavelength, like stars, and changes frequency due to movement has a Doppler shift, which is given the symbol Z, which can be measured by the following equation, okay, which you have to know. Where delta wavelength is the change in wavelength, okay, wavelength at the bottom is the reference wavelength, okay, so it's the wavelength on, say, planet Earth, and v is the velocity of the galaxy moving away from you, from Earth, and c is the speed of light. So question 1. Light with a wavelength of 400 nanometers, which is violet, of course, on planet Earth, leaves the galaxy, and by the time it reaches us, its wavelength has been shifted to 482 nanometers, which is in the blue. What is the Z for this galaxy? So using the equation, what is the speed of the galaxy traveling relative to Earth, and is it moving away or towards us? So pause the video now and see if you can get the correct answer or answers. Right, so the answer for Z is 0.2. So how did we get that? Well, it's basically 482 minus 400 divided by 400. Okay, so that's going to be, make that a little bit neater in terms of that, 82. Okay, so that's going to equal Z or 0.2. Okay, this is the change in wavelength, and that's the reference wavelength. The answer for B is 61,500 kilometers per second. Now, how did we get that value? Well, this is, again, you're using the equation delta change in wavelength divided by the reference wavelength, which equals V over C. Okay, so we've just worked out that as actually 0.2 equals V over C. Okay, so 0.2 equals 0.2 times C, which will equal V, which is the value 61,500 kilometers a second. Because, of course, C is 3 times 10 to the 8 meters per second. And the final answer is that the stars in that galaxy are moving away from us because it's moving towards the red end of the spectrum. Okay, that's redshift, which is quite apt since I'm using a red pen to write down the answers. So the stars are moving away from us as we observe their waves to be getting longer. They're redshifting. Okay, so if redshift happens as a source is moving away, what must be happening if a source shows blue shift? It must be moving towards us. So if a star system here, okay, is moving away from us, okay, you're going to see light moving towards more the red end of the spectrum, which is being emitted. And if it's moving towards us, okay, then it's going to be emitting more in the blue wavelength for the wavelengths it's emitting. So this is where spectrum and absorption lines are used for evidence. So looking at the light spectrum from a star is a useful way to identify the movement of stars and galaxies. If you pass light through a gas, some wavelengths of the light will be absorbed by the gas, forming something known as an absorption spectrum, which you'll look at in more detail in chemistry. Our sun contains helium, which we know because there is black lines of the spectrum of the light from the sun where helium has absorbed the light. These are known as absorption spectrum for helium. So every atom basically has these specific absorption spectrum, okay, where basically the element in the particular star has absorbed those particular wavelengths. So this is the spectrum for our sun. So how are these useful for us to tell how something, if a star is moving? Then if we compare basically a spectrum of our sun, which is close to us, compared to the spectrum of a distant star, which is not, then if the light source is moving away, the absorption spectra should look a little bit different, okay? And you can see actually what's happening to the absorption spectra. It's kind of moving towards the red. So why have these absorption lines shifted? Well, they've basically shifted towards the red end of the spectrum. This is known as redshift. Okay? So the faster a light source moves, the further its light will be shifted and the further away it is. Okay, so when we compare the light emitted from all different galaxies, a clear pattern emerges. Almost all the galaxies emit light from redshift. The further away a galaxy is, the greater the redshift, the further away and faster it's moving away from us. And we see exactly this pattern in situations that involve explosions, for example. Okay? Because when you have an explosion, okay, you've got a point here, then everything gets pushed out. There's an expansion away. You don't get particles moving towards the center. So this is kind of evidence for the Big Bang. So light spectra from different stars and from the edge of the universe show a redshift. This suggests that everything in the universe is moving away from a single point, the point of the Big Bang. Okay, this is observable evidence of the Big Bang theory. There is also further evidence known as the cosmic microwave background radiation. Okay, this basically is the energy that would be connected to the energy release of the Big Bang. Okay. In the 1960s, scientists detected this afterglow of the explosion in the form of this background radiation. As it was predicted, they are microwaves that can be detected in all directions in the universe, which is known therefore as the cosmic background radiation. And this has been detected coming from every direction in space. The reason why they're microwaves is because as the universe expands, these waves would become stretched and therefore they would reach much longer wavelengths than they had before. So they'd be in the microwave area of the electromagnetic spectrum. So in terms of reinforcing the knowledge, I'm going to give you a written task. Explain how redshift provides evidence for the Big Bang theory and what do I need to do. So explain in detail how redshift provides evidence for the Big Bang theory using the following keywords: redshift, galaxies, universe, expanding, initial point. And this is the grading. Grading of 1 to 3, you understand that the universe is expanding. Grading 4 to 7, you have briefly explained how redshift provides evidence for this. And grading 7 to 9, you have given a detailed explanation of how the redshift provides evidence for the Big Bang theory. So in terms of pair marking, the key points that your pair will be looking at is that light from most galaxies has been observed to be redshifting, moving away from us. The further away the galaxy, the bigger the redshift. The furthest galaxies are moving fastest. This shows that the universe is indeed expanding, and if the universe has always been expanding, there must have at one point been very small, the Big Bang. Okay. And this is again the grading system that you shall use. So let's look at a couple of exam questions, each worth 1 mark, so 2 marks in total. Complete the following sentence. Many scientists think that the Big Bang theory describes the origins of the universe, except the universe is expanding, but do not accept the origin of the Earth, because the Earth, of course, is a lot younger than that. Discovery of the CBR, or cosmic background radiation, was important because it proved the Big Bang theory, would be one thing it did. Okay, provided more evidence to support the Big Bang theory. Okay, remembering that theories require evidence to be proven, well, at least to be supported, sorry. And prove the universe will continue to expand forever. So any of those 3 points will give you the mark. So the final question, an exam question, is here are 2 visible spectrum from stars, including the dark absorption spectra, okay, where the atoms inside the star are absorbing energy. These lines are of specific wavelengths. Okay, so we have the absorption lines from our sun, about 8 minutes away, and also the absorption lines from a supercluster of galaxies known as BAS11, traveling at about 0.07 times the speed of light and about 1 billion light years away. So what is the name given to the effect shown in the spectrum from the galaxy BAS11? Only 1 point. Okay, let's see if you got it correct. It is, of course, redshift. Okay, because you can see the lines are moving towards the red. Okay, also will be accepted as the term Doppler effect or Doppler shift. Okay, which is proving, or at least evidence towards the expansion of the known universe.